Okay, it's 1 p.m. California time, Pacific time. So let's start. It's great to have Helen He with us today. Helen is a high-performance computing consultant at the user engagement group at NERSC. This morning we had a presentation by Rebecca. That they are in the same group. So over the years, Helen has worked on a variety of computer systems at NERSC. She knows a lot about parallel distributed computing, MPI, OpenMP, and also scientific applications. It turns out that many years ago, Helen and I used to be in the same group. The group was called Scientific Computing Group. That was morphed into other groups later. And so today, Helen will be talking about the resources that are available at NERSC, what you can find online, for example, and so you can use the hardware that's available at NERSC. And with that, Helen, please.
Thank you very much, Osni, for the introduction. I'm going to start to share my screen first. This page. I'm happy to give this class for the LBNL's Computer Science Summer Student Program. My name is Helen He. I am a consultant at NERSC User Engagement Group. I've been giving this training classes for several years now. And starting last year, we also decided to open this class up to NERSC users who are interested in joining to learn, for relatively newer users who are interested to know more about NERSC resources. And we're doing this virtually, starting for a couple of years already as well. So a few of logistics things first. Everybody is muted and you can unmute to speak. I'd like you to change your name in Zoom to first name and last name. You could do it, click participants and then more next to your name to rename it. So we could track who are in our session. And there's also a CC button that you could toggle and you can see captions on and off. And there's also a view for transcript that you could see the transcript real time and it will also be able to save it. We're using Google Doc for question and answers instead of Zoom chat. And it's easier to not be interleaved that we also have a record offline. We'll be mostly answering these questions in real time instead of typing. But if we have remaining questions, we could forward it to other NERSC staff because I'm not an expert on everything I'll be talking about today. They'll be posting slides and videos after this class. There'll be two places. That one is for a training event page and the other one is the summer student page. So if you have a NERSC account, we have added you to an NTrain 4 project. This is for the hands-on exercise later. If you can log in, you have to use multi-factor authentication. So if you have an account, however, if you don't have an MFA set up yet, you're welcome to apply for a training account. This is a link there. So some of these information have been posted in the chat, and we'll be repeating the link for Google Doc, the how to apply for training account in the Zoom chat, so you can find those information. This is the outline of today's talk. I'm gonna very briefly the NERSC and systems overview. Then I'm gonna show you a bunch of all the useful online resources that you can find about using NERSC systems and other resources. Then I'll talk about connecting to NERSC, a few mechanisms. Then I'll talk about file systems and data management, transfer, sharing with other people. Then software environment and building applications. Then more detail on running jobs that will be used for the later hands-on. And I'll also talk about data analytics software and services. So first, systems overview, NERSC systems overview. Many of you summer students attend this morning session, NERSC But for other people who didn't participate, just want to very briefly tell you that NERSC is the Mission HPC Computing Center for the DOE Office of Science. Our NERSC staff help to provide expertise, help for over 8,000 users and 8 projects, and lots of applications every year. There's different programs like biological, environmental, basic science, nuclear science, high energy physics. All these are open science at NERSC. This is a systems roadmap. Every 3 to 4 years, we deploy a new system. So right now on the NERSC floor is NERSC 8 Cori system. We'll be mostly using Cori for hands-on today. It has many core CPU. And then also Perlmutter is already here. We're doing the integration. So users are allowed to be on the system now, but it's still a pre-production system that and the configurations are still undergoing. So that's why we will be using Cori mostly for hands-on today. NERSC 10, the procurement is already underway. Have lots of discussions, meeting with vendors. And NERSC 10 should be an exascale system. This is a quick systems at NERSC. We have Cori and Perlmutter. Cori has over 9,000 Xeon 5 HK now many core nodes and 2,000 Haswell nodes. It was once it's still number 30 on the top 500 list as of now. And in 2016, it was top 5. And Perlmutter here has 1,500 NVIDIA A100 GPU nodes. And each GPU node has 4 GPUs and 1 Milan CPU. It also has the CPU nodes itself. And Perlmutter is top 8. It's in top 500 in June 2022. And last year it was number 5. So we're very proud that NERSC hosts these very advanced HPC systems here that we could, users could do the science on them. And the supporting resources like Ethernet, IP Fabric, the long-term storage HPSS, and there's other services, data transfer nodes, the Spin Science Gateways. I'll talk about a few of them later. So second part, I'm going to talk about online resources, lots of them. First of all, we have this classic NERSC webpage. It's www.nersc.gov. Just want to point out a few things that you can find news, that you can find science and publications there. And there's contact us. I think actually contact us is in the home or about. It's not a direct page. There's the ways that how you can find help with, how do you submit ticket, all these information there. And then the live status on that is MOTD, message of the day today, that you find status, which system is up and down. There is a section for users, and then there's a NERSC user group. We have a NERSC user group Slack, and you find information how to join Slack over there. And most importantly, training events. So it's also under for users and then NERSC training events and all the listed things there. And the one we're having now is Introduction to NERSC resource that on the bottom to get scroll down too much. And I would like just to let you know, if you haven't signed up the crash course for supercomputing next Tuesday yet, please do so if you're interested. This is mainly for training people to do parallel computing with MPI and OpenMP, and it's also a hands-on event. And we have a NERSC YouTube channel. So all our events, training events are recorded and archived on our training, the YouTube channel. And we also have professional captions for them ordered. They're not only just training events, but also other NERSC events like data science series and lots of computer science research talks that you can find there as well. So I have tried to put links to every page that you could follow afterwards. I mentioned about user Slack. You find it from NERSC user group. It's users helping users. It's efficient. It's not officially sponsored by NERSC staff, but we sometimes we would go look there and answer questions as well. If something urgent, do file a user ticket instead of relying on Slack though. And we also have implemented things called user appointments that you can schedule an appointment with NERSC support staff, and the different topics of appointment you can choose. They are 30 minutes each, like GPU basics, using GPUs in Python. NERSC 101 is like starting and basic questions you can ask. The major domain for NERSC documentation is called NERSC docs, docs.nersc.gov. Mostly these are technical documentations. And I like to point out one page called Getting Started. So it's mostly useful for a new user that you can find links, pointers to past new user trainings, and then links to all the useful link pages on the docs website. A few of things here, and on the left side, you can see all these bigger topics. I want it's all like lots of hierarchy layers, so it's not easy to find out what are the information here. So the search button is extremely helpful. If you want to find something, you can type it here and find relevant information. Here is one thing I just want to point out. If you're very interested to find all the related many layers even down, the whole tree of the documentation, this is our staff working page, but basically the GitLab that hosts the documentation. And it's open and it welcomes users to contribute contents as well. So here's the page, make docs.yaml. And I only actually copied 2 sections here, but you can see it's very detailed systems formatter here and using formatter Cori, and then one section says like development and programming model. You can see all the detailed lists. If you want to go visit that page, you can see the abundant hierarchy. Iris, if you are a NERSC user, you probably have already used Iris. This is our account management system. All the users, projects, user information, your allocation, whether you're enabled on which system are there in your SSH keys. It also handles multi-factor authentication. You can check your usage info as well. It's Iris banking or account management system. Here is a help portal, which basically you can submit user tickets, open a ticket. You can check all your filed tickets and your project's tickets. If the tickets is by default shared by your projects. There's also the request forms. If you have some needs to increase your quota, I want to make some node reservations, and there are a few more other requests there as well. So this is the help portal. Another page is called My NERSC. So My NERSC is sort of, you should log in and then see not only things like to the list of all the jobs in the queue or your jobs. There's a quick dashboard. You can see your quota, your active jobs, your completed jobs, and then you can see system up and down. You can find central information, central status, which system is up and down, and you can find past outage info, for example, and links to Jupyter Hub and to other useful pages. So next page I'll show you. My NERSC actually has link to lots of other things. From the left side, you can see like service tickets is just basically help portal, and Jupyter Hub is how you can access Jupyter through the web browser. And NERSC homepage, this is actually the classic homepage I showed first. Documentations portal is docs.nersc.gov, technical documentations. Accounts portal is Iris, so it's all here. And here is, I pointed out my jobs and quota and system information. So besides the main documentation page, we also have development systems or test bed. One of them is Cori GPU. So it's at a different location, docs.dev.nersc.gov. And this is you can access GPUs on access Cori GPUs. They are sort of individual system, but uses the same Slurm server from Cori. So you access them by logging to Cori. I'm not going to talk much about it. Some of you during summer may use this, but you're welcome to review this page and file any tickets if you need. Also, in today's, I'll be not talking much details about using Perlmutter, but I want to point out lots of related Perlmutter pages to you. So one of them is this Perlmutter system page, and you can find running jobs. And inside the system is one link called using Perlmutter, which is super helpful. And there's a application to Perlmutter readiness page, readiness page that has all the porting optimization. I have another page talk about all the Perlmutter page later. So here you go. Perlmutter training, sorry, I think I have a Perlmutter page at building applications where I'll have the Perlmutter related pages in the building and running job section. So here is the quick Perlmutter landing page and links to details and the readiness page. Also want to point to you lots of Perlmutter training events that have happened. One pretty complete using Perlmutter has Perlmutter system introduction. It has running computing on Perlmutter and has GPU usage programming models for GPU and Python, Jupyter, and deep learning on GPU. We have had NVIDIA HPC SDK is the complete toolkit for compile and NVIDIA tools profiling. And lots of others. We have programming with SQL, LLVM, OpenMP, OpenMP offload, OpenACC, CUDA. We don't have time to go over the details of using GPU today. Also, because Perlmutter is under rapid evolvement, so things will be finalized. Also, because of the limited time today, so we'll be telling you more about using on Cori, but lots of knowledge is applicable to go deeper on Perlmutter later on your own. Any questions so far, please? Let me check. Yeah, thanks, Madeline, for posting the links information here. I think I need to use another or maybe somebody can help me to read any questions on chat if there's any.
I don't see any questions here yet.
Q&A, yeah, if you can
Let's see
monitor
the
for me.
chat. So let's see the Q&A.
Oh, the Google Doc, I'm sorry.
No, yes, the Google Doc.
Permission. Yeah, Madeline, can you open it up, please? I think you
See any
created that.
question there?
The Q&A doc, right?
No.
The Google Doc, that's the Q&A Google Doc. Is that what you mean?
Yes, there's no question there yet.
Okay, so who says requires permission and requests aren't being approved? Maybe it's only for NERSC staff.
Or LBL?
Yeah, it's possible. So Madeline, could you please check the Q&A doc to make sure it's open to everybody and with right permission, please? Yeah, I could open it, so maybe it's for staff only. So yeah, so if Osni, you can access,
Let me
okay,
see.
we need to make it accessible to all so that people can ask questions. Before that, if you can access it, dude. Okay, Madeline is checking. Sorry about this. Yeah.
Oh, actually, as I'm a viewer, so I cannot edit either. So
Oh, okay, it's added. So can you change it to be yeah, whoever can edit. So meanwhile, just go on for connecting to NERSC. So if you have a NERSC account, we are using multi-factor authentication now. So you have to log in with password plus OTP, which is one-time password. you can obtain OTP via a Google Authenticator app or OSCE on desktop. Either way, it's fine. There's so the documentation is here, MFA. If you're here today, if you have an account, you may already try this and logged in. And if not yet, please do apply for a training account today. There's SH proxy.s that you can set up. So instead of you have to type password every single time with SSH proxy, you only need to do it every 24 hours. So it's much more convenient. Also, once you log into one NERSC site, it's transferable. Like if you logged into My NERSC, then later on when you go to IRIS, or later on when you need to log into Cori, it's also, they're all effective for 24 hours. So you don't need to type password for every single site. You do SSH, your username at cori.nersc.gov. For promoter is promoter-p1.nersc.gov or Saul. Saul is the promoter's first name, Saul promoter. So it's Saul-p1.nersc.gov. That's, you can do that as well. So you can username here, password, and then an OTP and a separate line. If it's a command line here, you type them in one single line. If you're having a NERSC training account today, OTP is not required, so you only need to type your password. And if you want to using visualization X forwarding, put -y in your command line for SSH. Then after that, if you say, for example, loading a GUI, say MATLAB, and you can just open up to MATLAB. So especially for X forwarding, if you're far away from the NERSC main site, it may take a long time. So we have a client service called NX, which also means no machine. NX, so we install NX on your laptop or your desktop. And then once you launch NX, again, you need a one-time password. It's so much convenient that X seems spontaneous, like no waste, no lag at all. And also it has an added benefit that if you, internet, say, suddenly is broken, you come back, or you close your laptop, come back later, it'll be at the same location as where you last time were on. So this is a quick NX session you can see. And once you're in NX session, you, without -y or anything, you modulo MATLAB, you can just open it up. And inside it, you can treat it as a regular terminal, regular X window as well. Then you can also access Cori through Jupyter, and inside Jupyter, one of the kernel is called terminal. So you access Jupyter with Jupyter Hub to this location, and then you log in. After that, you can choose one of the terminals as terminal and then treat it as regular. Actually, we have a pretty large percentage of users not doing command line accessing, they're using the terminal kernel here. So I'll be talking more about Jupyter a little bit later for other usage. Have we solved the Q&A permission now? Yes. Okay, great. So feel free to add any questions there. And Austin, if you see something you need to answer, can please just, I'll pause at each section and I'll ask if there are any questions. So
will. Sure.
Thank you. Are there any now?
No.
Okay, great, thanks. So next one is file systems and data management and transfer. So quickly, we have many layers of different file systems, and if the higher the performance, the lower the capacity, or vice versa. So we have tape drive at the bottom is the HPSS. Its data is there forever. Then community file system. It's also permanent, and it's usually it's for the project members to share files, and it's pretty large in quota as well. Then you have the Scratch. We have the Cori Scratch and Perlmutter Scratch. These are temporary because they are subject to purge, but they're much faster and large for I/O usage. The burst buffer is sort of on the node on Cori, but it's also temporary for job. And right now the burst buffer support is being reduced, so I'm not talking more about it. We had lots of discussion last year on how to use it, but this year we're gonna let it go. Here we talk about you have global home, you log in, you get landed on global home, and your project has the global community file system. Global home is really small. It's only up to 40 gigabytes per user. It's usually for you to, for your relative small scripts and some like README, or it's not tuned for perform for parallel jobs, and we do not change your quota. For community file systems, it's mounted on all platforms, so it's as well as global home, so you can access them on different NERSC systems. It's medium performance as compared to Scratch. The Scratch is recommended for most of your large parallel jobs. As I mentioned here, however, it has a 12 weeks policy, a purge policy. So make sure you save your data to either project directory or the long-term HPSS archive. We'll be doing some of the tests here today in Scratch. And this is HPSS. Everyone has access to it. And you would use the HSI or HTAR. If you have accessing it from any of the NERSC systems, these utilities have already been installed for you. You can just directly archive. But also you could install HSI and HTAR clients on your local systems and find out how to install them. So that you could back up your local data to HPSS as well. Or sometimes if you're not only a NERSC user, you could be an Oak Ridge user, and then there's also Oak Ridge, you can have HSI HTAR utility there. All right. So next section is software environment and building applications. So on NERSC, both of the Cori and Perlmutter are Cray or HPE systems. The OS is a version of Linux, especially on the compute nodes. And we have compilers on different systems, multiple variants. We have multiple compilers on each system. And our NERSC staff provide lots of libraries that you can use directly instead of have to build by yourself. We also have lots of ready-built application binaries like VASP, like LAMPs that users can also run. We have a big set of software stack by exascale computing. E4, I forgot the abbreviation for that. It's called, it's here, Extreme Scale Scientific Computing Software Stack, 4S, there's the 4S here. And there's also lots of the tools, compilers, libraries under the E4S package. All these, lots of the compilers or softwares are supported in the modules environment. On Cori, it's the TICO module. On Perlmutter, is the LMOD. They're very similar. So you log in, you do a module list. You can see the list of modules in your environment. There will be a default set installed for you or loaded for you. I'll show it in the next slide. And you can find which module is available, do module avail to find like module avail, that's CDF, and you can load a module, unload a module, load a module to use. You could use module show or module display to see what a module, what this module is about. What does it set? What does it set? Some paths, that is set some libraries, binary. And you could module swap between something like Haswell architecture to kernel architecture. I'll tell you what these are needed for our next exercise. And module help give you some help about what module is as well. So here's a quick list on Cori logging. If you log into Cori, this is, and you to immediately do a module list, you see like 22 modules are already loaded for you by default. Some of them are like lower level things users do not care much about, but I try to highlight a few. Like Intel here is the compiler, it's loaded for you. Intel is our default compiler on Cori, and it loads the Cray scientific libraries. It has like LA pack, scalar pack, some of the math libraries that you can use, link to, and the program environment Intel. So program environment Intel has underneath is a big umbrella module that it would load the Intel library, the Cray Lips scientific library. It'll load the MPI library here. This 21 is Cray MPitch, but it's like it's the Intel compiler built MPI library. So if you switch the program environment Intel to say program environment GNU, then looks like the Cray MPitch is still loaded, but it changes to the GNU compiler built MPI. Same for the scientific library as well. So it's like pretty modularized and transparent for users to switch between different compiler environment. And all this, the things you see will be very similar, but using a different mechanism of module. It's called LMOD parameter. So you want to say that when you build applications on Cori, because we have two different types of compute nodes, there's a Haswell compute node, there's a kernel compute node. So we are, and our logging nodes are Haswell. So when you try to build application to run on kernel compute nodes, we are doing cross compile. So the kernel binary won't run on Haswell compute nodes because the architecture is different. Haswell binary can run on kernel. Haswell binaries built on Haswell compute nodes can run on kernel compute nodes, but they are not optimized because you're not taking advantage of the kernel node architecture. And also, Cori binaries are not compatible to parameter binary. Parameter also has CPU and GPU, so there are different ways of building. So make sure you do binaries, build the applications differently and separately for each architecture. So I'll tell you a little bit how do you build for different compiler and different programming languages, codes. So normal, if you're familiar with some Linux systems, you're probably using any compiler. For example, if you use Intel compiler, you would be using iFort for Fortran, ICC for C code, but for the HPE systems, Cori and parameter, we actually have something called compiler wrappers. The wrappers are FTN for Fortran codes, little cc for for C codes, and capital CC for C++ codes. So whether you're using different compilers, you'll always be using the same compiler wrapper. But underneath, it'll invoke different, we call native compilers. So if you're under Intel, it'll invoke iFort for Fortran. If you're using GNU compiler environment, it will actually invoke gfortran when you're using the wrapper. The wrapper has this advantage that it also links necessary libraries, such as MPI libraries or scientific libraries. So we have some test codes here today. You will be using compilers. the wrappers also know where the include files are. So a little sample example script here is a bytest code Fortran. You use ftn and -o and mytest. Now you want to use Cray compiler. You would module swap program environment Intel to program environment Cray, and then exact same ftn command. On KNL, so by default, again, it's still Intel compiler. Now you have to swap something. This is the architecture. The module Cray PE Haswell is loaded by default. Default target architecture is Haswell. But if you want to build to run on the Cori KNL compute node, you need to module swap Cray PE Haswell to Cray PE Mike KNL, and then use the same wrapper to do the build. And then if you want to use Cray compiler to build an application to run on KNL, you would module swap PRG-ENV first, and then swap the architecture, then use the same wrapper to build. So this is about Perlmutter. I'm not showing exactly how you do it. So building for Perlmutter on CPU is pretty similar to Cori. It's loaded by default is the there's a Milan node architecture loaded as default, and the we have the GNU compiler as default. But other than that, it's very similar. There's also PRG-ENV GNU loaded by default for you. For the building on GPU, it's much more complicated. You'll still be building on the logging nodes, but there are different flags for different compilers, different programming models, OpenMP, OpenACC, CUDA, and different flags to use for different compilers as well, that to make sure you're targeting the GPU nodes. But this link, you can find much more information there, compiling, building software, Perlmutter. We also have, I mentioned that we have this GPU on Perlmutter readiness page. It's under performance category, and then readiness this is a very, very long single page, but has sections on GPU concepts, different programming considerations, programming models, running jobs, machine learning, libraries, IO, and even lots of case studies there. So it's this is like when we were accumulating knowledge by ourselves. We have a NERSC and NESAP team that especially focused on porting and getting user applications ready on Perlmutter. So this is the page that put down our best practices and knowledges that we learned along this road. All right, before I do the running jobs section, any questions so far?
I don't see any, Helen.
Okay. Yeah, I think we'll be doing this at hands-on part. We have more questions. Running jobs. So NERSC, most jobs are parallel. We have people using small nodes, number of nodes, all the way to the capacity, the full system. And we also have lots of serial jobs, especially for doing now HPC data simulation, data analysis, we call data intensive workload. That it could be a big bundle of lots of serial jobs, but could be tens of thousands of those in one set. And so we have a batch scheduler. It's called Slurm, and it's not first in, first out. We have we have queue policies try to be fair and try to have maximum utilization of the system. So we have two types of nodes. Logging nodes you would use to edit your files, compile, and submit your jobs. Could run very, very short serial utilities, not parallel jobs there. Do not run production jobs on logging nodes as well. And the compute nodes is dedicated resource, right? So here's a little diagram. On the logging node, you log in and you would use command either sbatch or salloc to submit your job to request compute node reservation, compute node allocation. And once you are gain allocation, you'll be landed on the head compute node. It's also one of the type of compute node that you asked for. And on that, you would run all these, typical commands inside your bash script, like ls, cd to somewhere, and copy a file, all those things. You'll be running sequentially on the head compute node. And at one point, because when you do ask for allocation, you actually ask for a number of nodes or for a parallel job. So you would use srun to launch your parallel job. And with this srun, you will be distributing your workload onto the multiple nodes that you asked for. So I'll show you a quick, my first Hello World program in the batch script. With Slurm, you have all sorts of sbatch keywords and asking for different resources. So I'll explain whether these are in next few slides, but you have a script you prepared for, say my batch script, and then on the login node, you would sbatch my batch script contains of the bash shebang and the sbatch slurm batch script flags and your srun command to do 64 MPI tasks of running this Hello World example. You could also run interactive. Instead of sbatch, you could say salloc, and then you would wait for your session prompt. Inside salloc, you do similar flags to asking for how many nodes, what queue you want to be, and interactive batch, usually you would do -q interactive. You're asking for haswell nodes for 10 minutes, and you would wait for the prompt. And then once it comes back, you would type srun, and you will see your output in the terminal session as well. This is called interactive batch. But again, for the batch script, so here -N is asking for how many nodes. You want 40 nodes for this request. And on the Cori Haswell, there are 34 physical cores, but there are 64 logical cores because each physical core has 2 logical CPUs. So each Haswell node has 64 logical cores. And when you ask for 40, here actually I'm doing little n is doing how many MPI tasks per for this job. So if you're not familiar with MPI OpenMP, don't worry yet. I think the next Tuesday's class will tell you what they are, how do you programming MPI and OpenMP for the parallel jobs. And for now, it's just we're talking about how to run these jobs. You don't have to know much details of the language itself, but basically MPI tasks is, so you have a big application, it's too big to run on a single node or a single physical cores. So you would distribute your application onto different and multiple physical cores. And in the MPI world, it's called how many MPI tasks I have to do my job. So here you have 40 nodes and we have 32 MPI tasks. We could run 32 MPI tasks per node. If we do that, then we will be running a total of 1,280 MPI tasks. And these -C and -CPU bind is critical so that your process binding to the physical cores are even and not wasted, not overlapping, so that they can be optimal. So we'll tell you how to specify this number of the C here. In the previous example, we're doing 32 tasks per node. That then, because we have a total of 64 CPUs per node, then each task will have 2 logical cores to it. This is the 2 coming from. Then the 32 tasks times 2 will be fully occupy these the node of 64 logical CPUs on the Haswell node. And then I mentioned about MPI tasks. Then if an MPI task asking for multiple cores, then underneath each MPI tasks, you can create multiple OpenMP threads. So it's a different combination of MPI and OpenMP programming model. Then in this case, like I'm again asking for 40 nodes, but I am only running 160 total MPI tasks, which means I'm running 4 MPI tasks per node. Then on the node of 6, we have 64 logical cores total, so that each MPI task will be using 16 logical cores. So here you have to specify 16. And again, to do CPU bind equals cores to make sure you're getting the best. It's called process and thread affinity, basically binding your MPI tasks, binding your OpenMP threads to the physical cores optimally, not overlapping, not underutilization, so that the cores won't have to split their memory or their CPU resources among different tasks. And then when you're using OpenMP threads, you can specify a few of OpenMP environment variables to further bind your OpenMP threads. So you would you want process bind to set yes, and where do you want to put your ONP threads, to the cores or to the threads. And here, because I'm running 4 MPI tasks per node, and I can run 8 threads per MPI task. This is for how many OpenMP threads per MPI task. Again, it's probably, if you don't know MPI OpenMP yet, you will get this knowledge next Tuesday, but lots of NERSC new users, they are pretty advanced in programming models. They're just new to NERSC resources. So here is the big template is useful for running jobs here. And I want to mention that we use Slurm here, and the way we do a thread affinity is sort of unique, that we use these flags. It could be different in different HPC centers. Right. And we have a page on affinity to tell you how do you set -C here. For Cori Haswell, there are 64 total logical nodes, and for Perlmutter CPU, the total is 256. Again, it's also 2 sockets Perlmutter CPU, but it's quite similar to do the affinity as compared to the Cori Haswell. So this is the page here. I mentioned jobs affinity. It tells it has formulas how to calculate the C values here, and and also gives a definition. The process affinity is bind MPI tasks to CPUs. The thread affinity is bind threads to CPUs, to those CPUs that have been allocated to its parent MPI process. And then there's also the topics of affinity here, the memory affinity, because for example, on Cori Haswell, there are 2 sockets, and then each socket is 1 NUMA domain, meaning the memory access from the cores on this NUMA domain, access to its local cores is faster memory. But if it needs to access memory on the remote NUMA domain, it takes much longer time. So you want to bind your affinity, bind your process thread to its local NUMA domain. So these are all being explained in the affinity page. We'll actually be doing one exercise on this. Here is quickly diagram. So on Haswell, the 2 sockets, socket 1 is socket 0 and 1. I would like you to pay attention to these numbers here. So there are 32 physical cores. These are black numbers. So each core actually has a number. So 0 to 15 is on the first socket, and 16 to 31 is on the second socket. Each physical core here, this is a physical core. It actually has 2 numbers to it. One is like physical core 0, also has a 32 number to it. 32 is its logical core. So if in one of the exercise, print each of my MPI/OpenMP thread binds to which core, it actually binds. It reports you I'm binding to the numbers. So if you know the number, you know if your binding is as expected. So the whole thing here is the top is one NUMA domain. It has cores 0 to 15 plus 32 to 47. And the bottom one has cores 16 to 31 plus 48 and 63. There are a few ways to check, how do I know these are my numbers, and the number of sockets, number of NUMA domain. These are the commands to find out. NUMA control dash hardware information. So I'll tell you on the compute node. Then on the KNL node, it actually has, we are doing this quad cache mode. KNL node has more other modes, but by default, we have set everything to quad cache. In this mode, there's only one NUMA domain. And on KNL node, we have 68 total of physical cores. They're numbered from 0 to 67. But then each of these have 4 hyperthreads, and then they're associated with different numbers to them. And then these are logical core numbers. So physical core 0 has logical core 0, 68, 136, and 204, all the way to here. So when we do the affinity exercise later, you will also be trying to coming back and compare with this slide to see if I'm binding my cores. Like if I want to have 64 MPI, have 16 MPI attacks, I would like to have the first 4 MPI attacks binding to these numbers. And if I have 4 threads each for these MPI attacks, I would like my first thread to be associated with these numbers cores, and my second OpenMP threads being associated with these, right? So understanding these numbers is useful. Here is an example script to run on KNL nodes. So as I said, we have total of 68 cores, but what if I'm running here, I'm running 64 MPI tasks here, then each MPI task will be on one physical core each. Then each one has 4 logical cores. That's what you set the -C for. And again, to set all these OpenMP variables. With these setting, you get very clean. Like I said, MPI rank 0 will be on core physical core 0. MPI rank 1 will be on core 1. And when you print the affinity, it'll tell you rank 0 has these 4 numbers. Rank 1 has these 4. And then also we are printing the thread numbers. Thread 0, 1, 2, each will be on 1. You see I color-coded. Thread 0 is of MPI rank 0 will be here. Thread 0 of MPI rank 1 will be here. On KNL node, sometimes because you have 64 total nodes, and if you say you want run 16 MPI tasks, will be actually on purposely not to use these 4, because otherwise they won't be distributed evenly. You don't want some of the MPI tasks being on because if a total of 272 logical cores, if divided by 17, 17 is actually happen to be divisible. Divided by 30, it won't be divisible. So it would purposely waste these 4 cores, and then normally people running MPI tasks in the power of 2. Most people do that. I've mentioned using salloc. So salloc have 2 ways of running it. One is debug, one is interactive. These are just different limits that we have for the jobs. Debug queue can run up to 30 minutes. And then you can have a pretty big number of nodes allowed. For the interactive queue, you have much longer time limit. You can run up to 4 hours, but only up to 64 nodes total of your project. And this also has a good advantage that if you either wait for 6 minutes, get a node, or it tells you, I don't have enough node for you. So this is highly recommended if you want to do a quick turnaround to debug to your applications instead of doing batch, submitting a job in the queue, and then you don't know when you have the results back. Again, lots of links here.
Helen, there are 2 questions.
All right.
Should I read them?
Yes, please.
Okay, what is the difference between batch, script, and interactive?
So batch is you prepare a batch script like script I've showed somewhere. This is a batch script. You give it a name and then you batch. Then your job is sitting in a queue. You wait for it. You don't have interactive access to it. So you can put in some of the things in, mail you when job is done, or you can constantly check in your job directory to see if it has been run. There's also a few commands you can monitor the queue. I'll show you in the slide. So that's batch in a batch queue, running the batch queue. Then the interactive batch is the interactive means you have interactive response to your job. You can have interaction with your job. What you do is on the terminal logging node, you do salloc instead of batch, and you wait for it. Like, for example, if you do an interactive, you usually wait up to 6 minutes. Either you quickly get your node, and then you will be on your logging on your head compute node, and then inside it you can do interactive batch running. You can do srun to do parallel run, because here you asked for 2 nodes, and then you have a session of 2 nodes. You'll be on the head compute node. You can run multiple batch jobs in it interactively, and you get the results immediately on your terminal. So these are called interactive batch using salloc. And the batch is regular batch.
Next question, Helen. That's a good one. How do you know how many cores you will need?
How many cores you would need? That really depends on your application. You would start from small input size. Okay. And then sometimes if you use too few nodes, you may be over the memory limit. You get stack fault, and you also get memory limit. You would actually get an error message of memory exceeded. But otherwise, you want it's code of balance. How many tasks you want, MPI tasks you want to use, and sometimes using too many MPI tasks, it'll actually decrease your performance because there's a lots of overhead of messaging passing each other to communicate. So depending on your problem size, you will find your sweet spot. We say that how many MPI tasks and how many OpenMP threads. And then based on that, you can usually fully occupy your node. Then based on how many MPI tasks, you would decide how many nodes, right? Maybe ask some of your colleagues for their similar applications, similar input size, how many nodes do they use?
There is another, would you take another question now, Helen?
Sure, yes.
Okay, so I have an application similar to Jupyter that has a GUI exposed over a port. How do I access this application GUI? It must run on a computer node only. Is it possible to open a port in this?
Compute node only GUI, that's on the salloc interactive batch, you'll be able to access it, GUI. So there's for example, there are lots of compute node access GUI, like debuggers, right? You have to run on a compute node. There are a few of the visualization tools that you want to do it, and also has the GUI. So salloc is your friend. I have an interactive batch. Right? Can I go on?
No, yes, you can continue.
Okay, I'll continue. So I did just say salloc is interactive batch. I was just to tell a few of the different ways of running jobs. So as I mentioned, there are probably many serial jobs you want to run, and you do not want to waste a whole compute node that has 32 cores in it. By default, our queues are exclusive, meaning if you ask for it, it's all yours. And whether you use the whole node, 32 cores, or you use one core, you'll be charged by the whole node. So we implemented the shared QoS, allows multiple people, multiple jobs to run on the same node. So you can run a small a serial job to use single core, or you can run a very small parallel job using a few cores to just submit to this queue shared, and you will only be charged a fraction of the node. You can also bundle your jobs. The bundle jobs is like, you can bundle them sequentially. For example, you ask for 100 nodes, and I told you you can use srun to launch a job. But if you want run 3 executables, you can run them sequentially, but then ask for a total amount of the wall time needed for each one of them. You can do it in a batch job like this, or in an interactive batch session. Once you get your compute node allocated, you can run one after another in the interactive session, of course, like this. And you can also bundle your jobs simultaneously, meaning you have 3 srun here, 3 basically parallel jobs, and you can run, if say one of them needs 2 nodes, another one needs 5. So in this case, you can run them simultaneously if you ask for total number of nodes needed for each. But make sure you put an ampersand and wait in here. Otherwise, if one of them finish, if they were, the whole job will fail without waiting for other jobs to finish. Okay. Then sometimes you need to do some dependency jobs, like my second job needs to wait for the first job to make sure it's succeeded. So you can do dependency inside. You can, this is job 2 job script. You can put a dependency after OK of your first job ID, for example. And then, or you could say after any means, as long as the first job finished, I will launch my job 2. The first one after OK means as long as first job succeeded, I'll launch my job 2. You can do it in the command line. You can also do it in your job script. You added this here. So you first submit first job and you get a job ID, right? And then you put a job ID here in your job script for your second job. This is called dependency jobs. There some of the workflows, for example, climate models definitely needed these dependency chains. There's also something called job arrays. You have many similar jobs, and it's the job arrays allows you to manage them much easier than individual jobs, because it give you a Slurm array job ID, and using this array job ID, you can manage similar sets of input files in different say subdirectories. Then so you can just it's and then these job IDs array there in the system, you can view them as one job to like monitor or cancel, but as long as they're submitted in the batch queue, they are allocated individually. So if you submit 10 jobs, it could be running one after another. They won't be run all scheduled simultaneously. So it's sort of array job is doing managing your workflow, right? So we do have some other workflow tools. I'm just giving you one example here. It's called in the next slide will be GNU parallel. But basically, what we want to tell you is that do not do srun one node, one core, my job, and then do a big loop. When you do that, it'll overwhelm the batch scheduler, and it's very inefficient. It could kill other people's whole Slurm session. So the parallel, GNU parallel is module load parallel. And on a logging node, you could say parallel -j, like in a sequence of 1 to 5, and then I'll launch 5 jobs. So this is very easy, very small overhead. It's even better than task arrays. So check out the workflow page. There are many tools for you to manage your workflow, whether it's sequential or small parallel jobs. We do have a job script generator to help you to put in some of your requirements, what node you want to run on, what how many nodes, what how long is the wall clock time, etc. And then how many tasks, MPI tasks, OpenMP threads, and I'll give you a template here. You can make some changes. You can add some more flags to it. And I'll adding some scripts here to pre and post processing, etc. But this is the template, so it's on my NERSC page, and in the job section, job script generator. It also has a parameter job scripts generator as well there. Monitoring. So I mentioned an S-batch, you submit a job, you don't know when this job is finished, but we have a few commands you can use. SQ is a Slurm native command, and we also have SQS, is NERSC custom wrapper script. Without typing anything, it gives you your jobs in the queue. If you push a -A, it gives you every user's jobs in the queue, and you can have another flags like -T, R gives you all running jobs, for example. And there's also an S account is to query the completed and pending jobs in the Slurm database, Slurm jobs database. We also have a monitoring. This is a documentation of these. How do you monitor pages, jobs? You could cancel your job. You could update your wall time, update some of the other flags for your jobs in the queue. So this is the page you want to check it out. On the web, my.ners.gov, you can see all the queues, queue backlogs. And we also have some statistics data, heat maps of the queue wait time. So for example, like a job asking for 2 nodes for 24 hours, usually for the past months, what is the historical average wait time? And you can see live status, the queue look here as well in the, I think, okay, yeah, this live status is not queue look. This is the MOTD. Okay, just a quick example here, the queue policies. So we have lots of queues. It's called QoS, is when you request what type of nodes, what type of service you want. By default, it's debug if you don't say anything. But most people have to use regular because it gives you much more longer wall time. The debugs only give you half an hour, right? Also, the max number of nodes is much higher than debug. But then if you want quicker turnaround, it charges twice. There's a premium QoS. And your PI has to approve you to access premium. There are the Flex QoS, you can request minimum wall time, regular wall time, and a minimum wall time that your job can be killed. But if your job has checkpoint restart built in using Flex, charging is half. And also, since you have asked for a minimum wall time, your job is much easier to be scheduled. There's a real time you have to get approval for, but it's a few set of NERSC applications that they need real time experimental data analysis, for example. So this is under special approval. Interactive, I already mentioned, usually for SALIC, interactive batch. So some considerations running jobs. I mentioned running jobs on parameter CPU is similar to running on Cori Haswell, especially regarding to affinity settings. Running jobs on GPU is much more complicated. The settings on flags of tasks, GPUs per task, number of tasks per node, and then there's a GPU binding flags as well. And there's a few of the CUDA MPI aware. There's a special environment variable settings. So we're not talking about this today, but the link is here. And compile separately, please. Also, do not run from global homes because IO is not optimized. Use Scratch for most of your big runs. And consider to use Shifter for large jobs that using shared libraries. I'll talk about Shifter in the data analytics section. Okay, so before that, any question on more about running jobs, please?
I don't see any.
Okay, so we'll be talking about this section before we do the hands-on. Data analytics software and services. This is a quick, this is about Cori's data feature. So when Cori was deployed, we want this to be serving traditional high performance computing plus data intensive applications. So we have adopted lots of data friendly features. So we have a large memory logging nodes. We have implemented Jupyter Notebook. And I mentioned serial queue that you can have a shared node to do to share a single node. We have a real-time queues for experiments, especially. We have lots of workflow management tools, and then also they will be running on the workflow nodes. Yeah, I didn't mention it specifically, but we have two types of big mem nodes. We have on the Haswell big mem nodes, and we also have an external large memory nodes that was added last year. I'll be talking about Docker, containerized environments. It's also data friendly. Compute nodes can have access to outside world, and you can streaming data to compute nodes, database access, etc. We have interactive queues here, and the data warp is for I/O acceleration. So here are the list of sort of software stack data related. Data transfer access, I'll be talking about Globus Online, and this is Jupyter. And this is no machine, not a machine. This is an X for the quick X window acceleration. We have Python, and Newt, and lots of workflows. I talked about the new Parallel, but there are Parcel, Papermill, Fireworks. Task Farmer is developed by a NERSC staff. Data management, we have HDF, NetCDF, Root, and different types databases that a user can request for: MongoDB, MySQL, PostgreSQL. And we have lots of data analytics and machine learning, deep learning frameworks. We have Python, R, Spark, Julia, MATLAB, Mathematica, TensorFlow, Keras, PyTorch. And the data visualization, visit ParaView. So I'm going to talk about a few of these in a little bit more detail. So this is the list here for Globus Online. So what is this for? Is for move data between different endpoints. The endpoints are mostly available for the ESNet or big data network. It's in many big HPC centers in US and Europe, around the world. So globus.org, you create an account, you can log in with your NERSC password and MFA. And the good thing is that you can find a endpoint that's already been set up. For example, there's a NERSC DTN endpoint. DTN is our dedicated data transfer system, data transfer node. There's endpoints for NERSC Cori, NERSC Perlmutter, NERSC HPSS. Once you are in this endpoint, the files on the system will be listed. So if you transferring data from two data points, the other one is, for example, is the OSCF the endpoint, then you can transfer data in between. You can archive from Cori to HPSS, You can also create a Globus Connect personal. So you can set up your laptop endpoint. Then you could easily move data between your laptop to our NERSC systems. So I have one for myself. It's called Helen's laptop. These are the documentations here. This is a quick file manager. Once you're in there, you can find one endpoint here, another endpoint here, and once you log in and you see your data, and then you can click one file here, and then click start from this direction, or if I click file here, use this start, and I'll move data the following the direction of your arrow. The good thing is that it does it in parallel. It does it. It is fault torrent, meaning if this got disconnected, it'll pick up afterwards. It will retry by itself, and I'll send you email once it's done. So data transfer tips basically use Globus for large automated monitor transfers. You can still do smaller, CP, CPU, or rsync for one time or smaller ones, but Globus is still good, also good for small transfiles as well. And then between those users, we have a little utility called give and take. So you can give somebody else in your file, and then that person will receive an email with a link, and then that person could do take-u from the sending person and that file name very easily. So if you want to have some, external collaborators, how do you share data with them? We have a few things. One is the web portal. So every single project has a project directory called global CFS. It's in the community file system, and CDERS / your project name, usually M something M2345. You could create a www directory there. And then in there, you could put indexed HTML or all the other things that you want to publish. Then these are just instantly available with this at this URL, http portal.nersc.gov/cfs/ your project. But if you want to do something more fancy, like you want some other users can access your data, also be able to do some, post-processing, downloading a subset of your input, doing some, even some analysis of your data. You can set up science gateways, and those are done by made within the Spring service. So there's a Spring service. In order to use this, you have to attend a Spring workshop. We are offering multiple times a workshop per year. You can easily sign up for one and have the trainings, and then staff will work one-on-one with you, make sure your science gateways are set up. Shifter. So Shifter is sort of a Docker-like functionality. Basically what we want is, because some of the applications, they want their own set of environment, and it's very hard to adopt them to bring everything they need, or that on ours, Cori or Permanent system, they may have different operating system, they may have a different complicated set of software they need. So for those, you can create a Docker image. And so that these users can just bring along and to run our systems. So with Docker, the problem is the Docker image. To create a Docker image, you need to have root access. So we can do that. The way we have is a sort of a little bit modified, and we have a NERSC as a shifter thing here. So for Docker, you still create an image. It's very similar to how you create it and from whatever OS. You do all these ways of you could run update packages, install dependencies, and then you build it. Then you actually made a Docker. Right after that, with this Docker file, you could build image, and then you would push onto the public Docker image, Docker registry. That's become public. But if you have a preference of make it private, the way you can do it is you could push it to our NERSC shifter registry. Once you have this shifter registry inside NERSC, once you have this shifter image inside NERSC registry, you can use it using integrated with Slurm commands. In sbatch, just add one line dash image equals your image name, and then you would load the shifter module, and then to run your application, you just add shifter in front of your application executable name. So this is very convenient to have your custom user environment. This is one example. It also helps, I think, in the running jobs last bullet, what I mentioned is that if you have a job uses large number of shared libraries, this is often the case for Python applications, has lots of like Python paths, the libraries is in many different directories. So once you create a shifter image for a Python executable and libraries, you bring them all in advance into the image. Then when you pull the image to the compute node, they're available immediately instead of you have to load image the shared libraries onto compute node. That would usually add a huge overhead. So here is a quick example. If you run one of the dynamic example was especially when the number of ranks are high, the time pulling the dynamic libraries into compute node is much higher. So using shifter versus using Scratch, this is the time, the startup time. It's only about a quarter of time versus 500 versus about 115 something. There. So that's shifter. Any pause we need? Any questions? There's a question about recording. Yes, we recorded. It's being recorded, and I'll process it before we upload it. Slides will be available quickly after the class is done.
So Heather, there is a question being typed right now. So
I'll continue and then go back to that.
yes.
So Python becomes much more popular, like compared to 10 years ago. Python has all these libraries that people use in data processing. Python can be used for machine learning, deep learning. So now it's fully supported in NERSC. We use Anaconda Python. There's a Python page on using parameter, but other than that, the things I want to talk about is applied to both Cori and parameter. So don't use user being Python, it's old. Use module load Python, it's much more updated. It's maintained by NERSC, and also it already includes basic packages, NumPy, SciPy, MPI4Py, for example. You could also make your own custom Python environment, module load Python, and kind of give it a name, Python version, kind of activate, and then you install your custom packages, and then use it, and then deactivate. So here's a page and a link to how to run Python jobs at NERSC. There's much more details there. Different ways of using Python, using module, use your own custom version, and then how to run parallel. It also has something about how to run Python code in parallel. This is a page. So you have a few ways. There's multiprocessing. For example, if your Python code calls some libraries like MKL underneath, and it'll use a number of threads available to do multiprocessing. It's sort of like a black box. Then recently we have just configured PyOMP on parameter. It's not ready on Cori. There's a page on PyOMP. You could use some of the directives similar to OpenMP in C and Fortran, but you can use those in Python code. And with this PyOMP counter environment, you have to create following instructions there, and then you're able to actually setting number of threads to run your OpenMP, PyOpenMP code. There's a Dask is a framework. You could create a group of workers that has its own scheduler to run on single or multiple or many nodes. Dask has its own visualization tools, so it's also useful for parallel Python. MPI for Pi definitely has MPI in it. You have to install following instructions, the Pi for MPI for Pi, and it's best to use with Docker and container. But read the instructions here, and Pi for MPI for Pi on GPU also uses CUDA-aware MPI, so it's has more hooks in using it as well. But you can find the documentations. Our Python support at NERSC is excellent.
Hey, Helen.
Yes, question.
Good question now. Okay. Would you typically suggest that shifter images of a Python application would have better performance over CVMFS installation of the same application?
Over CVMS. I don't have this knowledge or quick answer for comparison, but for little bigger Python applications, especially in large jobs of Python, number of ranks, for example, the using shifter image is much better. I heard for Pi for MPI, it's recommended to use shifter because the huge number of shared libraries with the large number of ranks, it takes so long to start up to make them available on compute nodes. For actually, I have a plot quickly show you here. Do you see that? It's not CVMF, it's a tempfs. So CVFMS, I believe it's already a shifter environment. So CVFMS is provided NERSC as a shifter environment. It's not on its own. So if you have I'll take it to the Python support people and CVS support people to see if they have any comparison data. And I'll leave it the answer in the Google Doc.
There is another one here in the chat that I pasted also in the Google Doc. Can we use Ray distributed library for running parallel Python code on NERSC CPUs and the GPUs?
I think so. Yeah, I think Ray was one of the package framework here. Check the documentation.
Please go on.
Okay, so I just said Python and yeah, talk about this. And Jupyter, almost done talking. Then we have about half an hour to do the hands-on that as planned. What is Jupyter? So I'm sure many people have used Jupyter in various occasions. It's a sort of notebook. You can create and share your documents. People using it for live code, equations, doing visualization, people doing it in the training. And you can use notebook for machine learning, deep learning, tutorials, all sorts of things. Very popular. People using Jupyter to log into our system without command line logins as well too. So here are the available Jupyter kernels. Besides the things available provided by NERSC provided, we have a Python kernel with Julia, lots of machine learning, deep learning. I think in the Python section, I also talk about how you. Oh no, I'm going to talk about. You can also create your own kernels to be used in the Jupyter kernel. It's very similar to a setup for the Python Conda environment, but except you're creating something especially for IPy kernel. So here's the instruction to build your own kernel to be used for Python. So you modulo Python and then create, make sure you have IPy kernel plus all the other packages you want to install, and counter activate my env. And then you have another step to do. IPy kernel install --user --name. This is the name. My env Jupyter is the one you're gonna see in the Python in the Jupyter available kernels. As here, I have my env. These are my own Jupyter kernels. So you could make up those on your own as well. So additional customization. What if you want much more complicated? For example, I want my kernel have some environmental set. I want my kernel to have a module being loaded, etc. For those cases, you can create a script first, helper script, and then I think this is Jupyter's file, and then using this file, I think I'm missing a few lines here to use this file to create the PyIPy kernel. A few of the steps are similar to the conda create steps here, but using the file and using the helper script. I'll add those to the slides. Okay, and then when you log into Jupyter Hub, you will see as this, I'm using a train account here just to show you. You see parameter, you have shared CPU, exclusive GPU, and configurable GPU as you have more custom settings for those. And Cori, by default, you have shared CPU. And I actually, normal users don't have this button here. This is for the Cori GPU access. You have to specially request for the Cori GPU access, then you will have this button. And you could also request for exclusive Cori CPU access. Then you have another button here. Then you could just launch, choose a start and choose your kernel, and then just use the Jupyter Notebook after that. Deep learning, machine learning stack. This is a big page, machine learning. Some of the big, so we had a survey, which framework tools are you using? Scikit-learn is part of Python. Then Keras, TensorFlow, and PyTorch. So we support all of these, and with different training libraries, and we have them available in Jupyter and Shifter. So if you use not using Jupyter, then you module load a version and pip install, and you can install your own packages with conda create. And we have some pre-installed Jupyter kernels like these, like TensorFlow here, different versions, PyTorch, you can see that. And you can also use your own custom kernels, like I mentioned for the Jupyter, how we did this for the Jupyter kernels. Right, we're right on time for the half-hour hands-on. More questions, please?
Let me check quickly here. Oh, there is one person typing right now.
Okay, yeah, I'm sorry with very compact presentation, because normally we have a new user training, it could be like a day's worth of things.
Okay, this is the question, Helen. Can we run Rust code on Cori or Permuter?
Rust, I'm not familiar with that, I'm sorry. I'll find out and answer that in the Q&A doc.
All right, so then go ahead, Helen, please.
Another recommendation is if you want to create a ticket, we could route to the more acknowledged staff person that are expert on the data analytics. So we will be doing hands-on exercise today, doing compiling and running jobs on Cori. So if you have a NERSC account, make sure you can do MFA logging to SSH user at cori.nersc.gov. Training account, just use your password. The NERSC account user use MFA to logging. Then I recommend you go to Scratch and then git clone and a CD to that directory. We have 3 exercise README files you could follow. And we have a reservation today from 2 to 3:30. It's half hour past the end time. You're free to leave at 3, but if you have more questions, I'll be staying until 3:30 to answer any questions, with also reservations still available. So in the README file, it does say so. During reservation time, you would have these two flags. The reservation could depends on whether you want to use a Haswell node or a Kernel node. And everybody's in this project. Don't use your regular NERSC project if you are a user, because the reservation is only accessible from this account. We also have some available batch scripts. In there, you could batch directly, but you you could also use salloc to do more experiments with these affinity settings. You can see the results right away. So follow the README, please, and let me know if you have any questions.